Welcome back to Risc-V emulation in a high-level language. Uh, Last time we tinkered around with file I/O. We were able to read and write from files. Everything is wonderful and good, but as I started reviewing the code for the next step, I realized that it's time that we revisit some of the design of the current project. And the reasons will become evident once I describe the situation of the current situation of the emulator. So on screen, I'm showing a crude diagram of the current state of the emulator, where we when we when we build our programs in memory, we first allocate a chunk of memory at address 0, and we mark it as read, write, and executable. And then we use the assembler piece to inject code and data into this chunk of memory, and then when we run the program, we also set up a register, the R2 or X2 register, to point to the end of that same chunk of memory, and that becomes the stack of this program. And while that is, perfectly fine for prototypes and to get things started, it becomes problematic once the program becomes larger, and also there are some security concerns. For instance, one observation is that because this chunk of code is both readable, writable, and executable, it is possible to construct data on the stack and then uh, fool the emulator to execute the data on the stack. And this is a very serious security vulnerability that we don't want our emulator to have. Another one is that the address of our data or code has always been at address 0 and slightly above 0. And the difficulty with that is that a very common mistake in programming, especially low-level programming, is that you are using a null pointer, that is a pointer whose address or whose contents is all zeros, and then you try to access the data through that null pointer. And the null pointer is supposed to be an area of, or an invalid memory address. In essence, attempting to read or write through that pointer should cause an exception. So we need to address these concerns, and in order to do so, we're going to have to change both the assembler and the linker and the emulator so that they can handle the desired layout, which is what I'm showing at the bottom half of the screen, where we start by making sure that the address 0 is not mapped to any memory at all, which means that if we try to access that memory using a pointer that has been initialized to zeros, then we will get an exception and stop, which is correct. That's what we want to happen. Secondly, we want to separate the stack code and data from each other because we don't want them to be um, uh, potentially overwriting each other. And the general idea is that we will create separate sections for each one of these, where each section has different attributes. The code section where our data, where our program is, needs to be executable, so that will be marked as readable and executable, but not writable. We don't want the code section to be writable because that would allow bad things to happen. You can modify the program that is running and make it do things that it was not originally designed to. Now, there are some scenarios where self-modifying code is completely acceptable, but we're doing this for illustrative purpose. This is the normal situation in most of the executables that you run on a day-to-day basis. The code is readable and executable, but not writable. And then the data, and I've forgotten to annotate it here, but it needs to be readable and writable. But we don't want to execute data. That should be an error. That should be an exception. That should stop the emulator in its tracks. And similarly, the stack, we also want to make it readable and writable. And we also want to use a little nice feature here, which is that if the stack, which is, as you may recall, is growing towards lower addresses in memory. So if I add a stack item here and then an item here, eventually when I run out of stack space, I want the memory that is below those addresses to be unmapped so that if I try to access that memory, I will get an exception. So in order to accomplish all these goals, we have to redesign the way that the assembler and the linker and the emulator work today. Now, if we go back to our project and look at the main program, you'll notice that the main program at the very beginning, it allocates a chunk of memory, which we hope is going to be large enough for our project. And then we create the memory object, including that bytes into, well, we inject those bytes into the memory object. And if we look at the constructor of memory, we'll see that it puts that at address 0 and gives it the attributes read, write, execute. And then uh, that memory object is passed around. It's passed into the assembler, where the assembler modifies the memory and writes to that 0 page. And then later on, we have our linker, which is resolving all of those symbols, forward references to symbols. It also takes the memory as a parameter and mutates it, uh, doing all of its patching. And then at the end, uh, the same memory is being passed into the OS emulator and the emulator classes. So this memory class is doing a lot of work. So, and we want to separate the concerns here. We want to make sure that the assembler doesn't have to worry about what exact memory addresses everything is at. Uh, by giving it a memory object with actual addresses already at this early stage, we're committing early to address 0 for our objects, and that is not what we want. So what I'm going to do is I'm going to introduce an abstraction. I'm going to introduce a new class called assembler section, which I've already written over here. And the assembler section is a class that contains a couple of operations that the assembler needs when it's writing. It needs to be able to write bytes, an arbitrary number of bytes, and it needs to be able to write an arbitrary number, sorry, a little endian word. And this is used when we're emitting instructions. So this would be used to emit an instruction. We also have an overload to handle signed integers, which just simply casts them to an unsigned integer and continues. Um, so the assembler section stores all of the bytes that are being written inside of a memory stream. If you're familiar with .NET, you know what this is. If you're not, I'll briefly explain. A memory stream is like a file stream. It behaves like a file, except it's all in memory. So what we can do is we can create a new one, which will be, it's the same thing as creating an empty file. And then when we write the bytes, we place our position at the beginning or at a position inside of that stream where we want to write those bytes. And then we issue a write call, just like you would write to a file. And so what will happen is this memory stream will slowly grow as the assembler runs through and assembles instructions. And in the end, this bytes collection can be extracted using this call bytes to array. And we can return to a caller the assembled bytes, the bytes that are the result of assembling the results of assembling the program, but there is no notion of memory per se. The program memory is not in play here. Then what we want to do is take the linker, and if we look at the linker today, when it accepts a memory, we were going to change that so that instead it will accept an assembler section. And in a possible future enhancement, it could accept multiple assembler sections. But the point is that we no longer feed it a memory. We're going to give it an assembler section and an address. We're going to tell it where we want the base address of our program to be. And then when the linker then does all of its relocations, that's the point where we create the actual memory. So the memory will be created inside of relocate. And then that will be returned to all the emulators, the OS emulator and the Risc-V emulator, so that they can then modify and read that memory as they wish. And in particular, if we go back to the program, one of the things that will happen then is that once the program is loaded into memory, then after the linker has created that memory, then the OS emulator and the Risc-V emulator will be fed a memory that will be augmented with an extra section, which will be the stack section. Okay, but let's stop talking and let's start coding. The first thing that we wanted to do then is to change the assembler so that instead of consuming a memory, um, we will instead create a segment and or assembler section and use that instead. So we'll stop passing in this parameter. We will assume that we are the ones who create this parameter, and I'm going to change the type of this to be assembler section instead of that, and then I'll say new assembler section, just like that. Now, and I've cleverly designed the class assembler section so that all the methods that we were calling on the memory object previously, we're now calling on the assembler section, so the methods are named the same. Okay, so then we want to give the linker an opportunity to access the assembler section. So we'll need to make this a public method, or a public property, I should say. So let's first change this to public, and then let's rename it to section. And then let's make it a property. And then let's put that along the other properties of this assembler. Okay, nice. So now we have exposed a new property called section, which contains the bytes that we're assembling. There are no other changes needed in the assembler itself. Okay, so now let's go over to the linker, which will now be changed so that instead of accepting a memory, you will be accepting an assembler section. So let's pass that in, assembler section, and then we'll also want to pass in a base address. So we want to tell the linker that take that section, and I want you to put it at the following address, and we'll give it an address as a parameter. And then when we create the, instead of using an existing memory, we will now be responsible for creating a memory. So we'll say this.memory equals, and then new memory. And then we'll say this.memory allocate. And we'll allocate a piece of memory at the address uadder. And what are the data that we're going to be putting into that address? It's going to be the contents of the section. So we'll say section.get assembled bytes. And then finally, to maintain compatibility with existing code base, we will continue to do access mode read w execute. But the point is that now in the future, we were able to change this to section attributes, which I haven't talked about and are not in the scope for this session today. All right. So now that we have done this, we want the relocate method to return the memory that we have generated in the linker. Okay, good. So that should do that. So right, so we're pretty much done here. But now we have to compile our program, and we'll find that nothing builds because we have changed the interfaces of two of our classes. So we need to fix all those build errors. And the first ones are here. Now the assembler no longer takes a memory, and in fact we no longer create the memory at all. The memory is being created by the linker. So down here someplace we will say var mem equals linker relocate, and then the linker needs to take the assembler's the assembler section like this, and then also it needs a start address. Let's or a base address. I'm going to call it base address, and then at the top of our program here we'll say var or const uint base address equals 0. Again, this is to maintain compatibility with our existing program. We will make the changes to reflect the desired state later. But for now, we're just trying to make the thing work the way it did before. I'm also noticing that these two variables are not used, so I'm just going to discard them. Let's get rid of that. All right, so now that those are done, let's try building again and see what else is failing. Okay, so that fixes those issues. Another issue that I noticed while I was looking through the code is that this string here is not null terminated, and that's going to cause a problem. The reason why it wasn't causing a problem before was because the memory that we allocated before had ample extra space. So as our assembler was writing these bytes into that ample extra space, at the end here, there would be a 0 in any uninitialized memory. But now when we're using the stream, we are in effect stopping the memory right here. So there is no more memory to be read. And so what we need to do is tack on a 0. And the reason why I do it this way is because I have this literal string modifier on this string here, and the path would not work if I... Well, actually, let's do this. For our Unix friends, we can change the path separators like this, and then make this one big happy string. This will work both on Windows and on Linux. So let's switch that over like that, and that will now properly be null terminated, because remember, our strings are null terminated in our ABI. Okay, so if I try to run this, what happens? Let's find out. Well, it looks like our program still works. That's great. But we violated a big principle here. We haven't actually run any of our unit tests, so let's make sure that we can run them still. And I'm expecting these to now start failing. And indeed they do, because we've changed the interfaces of our central classes. So we need to fix our unit tests. So we're inside of assembler tests now, and here the memory object has now disappeared. So we get rid of that. And then given memory also goes away because there's no need for it. Instead, what we need to do is when we run one of our unit tests, we create the memory afterwards. So let's do that. Now, these are testing the assembler without the availability of a linker. So what we want to do here is just take the output of the assembler, which is the section, convert that to the assembled bytes, and then use that instead of that. Also, let's be consistent throughout and not use that constructor where we pass in the memory. Instead, what we'll do is we'll say memory.allocate bytes at address 0, pass in the bytes themselves, and then some attributes. This would be a read and execute attribute. Okay. Well, that should do the trick. Now let's find the next error. No problem, Sam. I disagree. It looks like it doesn't build the unit tests when I type the build command. So I'll have to just run the tests themselves. Okay, so here's our next class. It's the emulator. Now the emulator, again, we will no longer pass in any memory to it, and that will fix that problem. And then here, oh, here are a lot of memory objects that we don't want to use, so we'll get rid of that, get rid of that. And here, what the whole purpose of this is to compare the output of the assembler with the output after the linker has had its chance. And so what we need to do here is do the same trick that we did before, which is to allocate memory. And so the way we allocate memory from the assembler and make that mem. So instead of doing this, we will do var mem equals asm, actually new memory, and then mem.allocate at address 0 the memory that came out of the assembler, which is asm.section.get assembled bytes, and then access mode read execute. Now for the second time that we run this, we want the linker to generate the memory too. So we will pass in the asm2 and the address of 0, and then asm2, sorry, section, and then this will return mem2. Okay, let's try running our tests again. This will still fail. Still have a few more places where we need to fix our logic. Okay, so everything compiles, but now we have some unit tests that are failing. Let's take a look at those. So here's the first failure. And what's going on here? We're looking at the disassembler. And the disassembler is saying that we're running this program and it's running on a chunk of 16 bytes. But the problem is that these two assemble instructions, which are 4 bytes each, only amount to 8 bytes. And we need 2 more words of padding in order to make it to 16 bytes. Or we can change the disassembler to just disassemble 8 bytes. So let's do that instead. We'll do that. That should hopefully fix that problem. Let's see if that indeed was the case. Yeah, so remember, the reason why that was previously passing was because the memory objects that we were creating were always 1024 bytes and filled with zeros. Here, when we're running this new assembler, it will only generate 8 bytes of assembled data, and so we have to stop our disassembler from trying to disassemble data that doesn't exist. Now let's take a peek at the emulator. Almost everything is failing. That's bad. Now, why would that be? Let's take a look at one of these failing tests. And what is the actual failure? The failure is that the registers don't appear to have any correctly initialized values. Okay, that's interesting. So why would that be? And this one we probably will have to, well, let's take a look and see what run test does. Ah, okay. So run test creates an assembler, and then it runs the test, and then it runs the emulator. But where did the emulator get its memory from? It gets its memory from over here. We create a memory, and then we initialize the emulator with that memory. And this is long before the assembler has had a chance to build the program. So this is not going to fly. So what we have to do is change the run test so that these steps are happening at the run test, inside the run test function. So what we'll do is we'll discard these because these are getting in our way. And instead what we'll do is we'll steal some of this code and then find our run test method, which is over here. And what we'll do now is, instead of relying on a previously created memory object, we will now create it ourselves and then initialize it with the output from the assembler. And because we are emulating the code in the old the old code emulator was making assumptions that the all of memory is readable, writable, and executable. So we have to continue with this, even though it is unpleasant. In a future revision, maybe we will change the unit tests so that they don't depend on this. We also need an emulator for the OS. And then the actual emulator is here, and then we'll change this to mem and mem. That looks good. All right. The next problem, though, is that we have a timing issue, and that is that we run our test builder here, but we, inside of our tests, we then expect the emulator to be available. And the emulator is not created until after um, run test has executed this lambda here. So if we go back to run test, we want to feed register data into the emulator, but the emulator does not exist yet. It only exists here. So what we're going to have to do is we're going to have to create a register bank object in this unit test and then feed those registers, the pre-initialized registers, into the emulator. Now let's take a look at the emulator and see what it does. So as you can see here, it creates the space for the 32 registers, but maybe we can create an overload of the emulator. Let's copy this constructor, and let's have this one call itself with the memory and the OS emulator, and then an array of 32 integers. And then we'll change the other constructor so that it accepts an array of registers. And then what we'll do is we'll say if registers.length is not equal to 32, then we throw an exception. Like that. Good. And now what we'll do then is we'll initialize the registers like this. So now we have the capability of either starting an emulator and letting it create its own registers, or we can pass in our own register bank. And so now we go back here and we say we want to have our own registers. And then every time we run a unit test, we initialize this to a new bank of registers. And then all the places where we're calling emu.registers, we will now instead call this.registers. So let's fix that. Okay, good. And now we have another problem, and that is that the memory that we are writing for our unit tests, well, the memory does not exist yet. So instead of doing these write byte instructions, which actually were written before we added the define word assembler capability, we can now use define word to define this word in memory. Notice how these words are always written at address 8 in memory, and so all we need to do is make sure that we have those bytes at address 8. And the way we do that is by writing first a dummy word. Now this is an assembler. It starts at offset 0. This is offset 4 because instructions are 4 bytes. We write a word of 4 bytes of zeros, and then finally we write the actual word that we're testing, which in this case is little endian. Remember that we write the low bytes first, so we write 78, 56, 34, 12. That is this word, 1, 2, 3, 4, 5, 6, 7, 8. So now we can remove these statements. And that should do the trick. And then we have to do the similar job for the other unit tests here. So we'll write a padding word of 0, and then this is 8765. We might as well copy this. Okay, that was good. That fixes that problem, and then we have another issue here. Let's fix this. So again, write a word of zeros, and then here the word that we want to write is the same as the one before, it looks like. So we'll grab that. And we still have some more failures. Here's a single byte at address 8. Same procedure though. I'm glad that I was very regular when I wrote these unit tests. I'm using the same pattern. Makes it easier for me to fix the unit tests. Okay, and then we get rid of that. And let's try running our tests to see how many errors we have left. Okay, we still have quite a few. Aha. Okay, so this is a specific unit test where we create a chunk of memory that is not executable. Yeah, we create a chunk of memory where we have the memory is only readable but not executable. And we want our emulator to stop when that happens. So what we'll do is we will have to change the run test function so that we can pass in the attributes of the memory that we create when we run it. So let's add an optional parameter to run test called access mode. And in this case, we'll make it read. Let's go to run test. And we'll add an optional access mode. And make its default value RWX, which is what most of the unit tests are expecting. And then instead of using access mode RWX hardwired, we will use the access mode that is passed in the function call. So now we have gotten rid of that particular error. And then here we have another test where we want to do the LW0 to get us to address 8, and then at address 8, define W. Define W, here we write an 82. All right, and then we can get rid of this statement. Now here, we do want to hang on to the memory in our class. Okay, so we will do this, private memory default. And then when we create our memory inside of run test, we will make it a member variable, like that. So now, let's make it super clear what we're doing here. The older I get, the more I use the explicit this. Okay, are we building? Let's give it a try. Let's see if we can pass all of our unit tests. No, we're still seeing a lot of failures, so let's take a look and see what the problem is. Okay, so what gives? What gives? What gives? Ah, yes. We added the capability to pass registers, but when we create the emulator, we don't actually pass the registers. So it will create its own registers, and so none of the tests will pass. That's okay. We will fix that in our run test function. So here, the emulator, as you can see here, is not using this start registers. It's using its own register bank, which means that we have no way to inject our own registers into the emulator. Now we are. So these are our registers. We pass them into the emulator. I'm assuming or hoping that that will fix most of the errors that we're seeing. Okay, that's a big improvement. So we still have a few more errors. Let's see what we can do to fix them. Um, so let's find what is the issue here. So we were expecting, oh, here's the same problem again. We're trying to read from a higher address this time. We're trying to read at address 128, but the assembler is not going to make memory to address 128. So how do we fix this? Well, what we can do is we can just fill in a bunch of padding bytes until the assembled chunk of code is um, for, well, let's see how many, 128. So let's do 128 words. Actually, we don't even need that many, but let's just do this. This is more padding that we need, but the padding will make the assembled chunk of memory bigger than 0128, and this should cause the unit test to pass. Well, in fact, let's be a little bit adventurous. Let's do this. Let's say that we want to do this. That should pass. That memory should pass. Let's try it. Oh, still failing. Right, let's maybe make it bigger. Let's make it 128 then. Yeah. Let's run that again. Okay, now we're passing. So this is a question of making the padding after the store instruction here large enough so that this memory becomes valid. The issue with that we just fixed will be present in store byte as well. So we'll just do the same thing. We'll do a define word. We'll define a bunch of zeros, and let's make it just the same size. And then SB and SH has the same problem. We will pad it like that. All right, let's run all the unit tests now. So all the unit tests are now passing except for this one. Disallow if not executable. Let's see what the issue is here. The issue is that we are at this statement assert fail, which is happening after the run test. And the whole idea is that we're not supposed to get this far because we're trying to execute read a memory that's read-only, not executable. And so we were expecting our emulator to stop executing when it reaches this point. So let's take a look at the emulator code and see why that would be. So let's find the exec function. So what this will do, it looks reasonable. It's saying while the memory that I'm reading is accessible, read that memory and then do your thing. But the problem here is that suppose that the memory that we're trying to read is not executable, then this will fail, the while loop will fail, and then we just return -1. But our code, our test, previously was expecting this to throw an exception, invalid operation exception. And it's not doing that. It's returning -1, and that means that the run test completes, and then we end up asserting that, or well, basically forcing a failure. We should write here expected an exception because the memory is not marked executable. Okay, so that explains why we have an assert fail there. So how do we fix this though? Well, the emulator was written a long time back, and during that time the design has changed. We introduced the notion of memory protection, and so now when we do a read, we always check to see whether we have access. So what we could do is we could change read to have an overload where we pass it in an access mode that we expect to be able to, well, that we want to use when reading the word. And if that access mode is not satisfiable, then that should throw an exception. So what we'll do is we'll add an overload to read word 32. I'm going to call it read LE word executable. And then put a comment here to explain that use this when reading instructions for execution. All right, so we'll do that. So in that case, we want both read and execute. Otherwise, the logic is the same. Nice. So now we should be using that. And there we go. If we run this, oh, we're still failing. Let's take a look at why. All right. So we have some other, oh, right. The reason for this is because the emulator, no, wait a minute. Let me think about this. Mm-hmm. All right, let's take a look at what's going on here. I guess we'll have to debug this. Access mode is being initialized. Let's verify that that indeed is correctly initialized. So let's run this under the debugger and find out what is going on. So here we are. Access mode is read. Okay, good. And then our emulator is kicked off. We give it a bunch of registers, and then we check. Ah, we still have this while loop. Okay, I need to get rid of that because that access check is being done inside of this function, read word executable. So this just becomes an infinite loop. And the only way to execute or leave this loop is either throwing an exception or executing the instruction 0, which we, as you may recall, are treating as a break instruction or a stop instruction. Nice. All right, let's try this again. Run all of our unit tests. Oh, now we see a bunch of failures. What are these? Okay, so now we are unhappy because the page that we're reading is, no, oh no. Oh, we'll need to debug these as well. So let's, oh, I see what's happening here. What's happening here is that with our new assembler, the assembler, yeah, the assembler is generating the minimal amount of bytes required. The problem is that we're depending on all of our emulation tests to always have a byte of zeros at the end of the code. And that was done before because the way that happened before was we allocated the memory ahead of time. We had 1024 bytes of memory. We assemble into the first few bytes of that memory. All the remaining bytes were zeros. And then once we executed the first instructions, we would hit the zeros and stop. But now there is no more bytes. So what we need to do is in the emulator, when we build our tests, we need to ensure that there's a minimum amount of or at least 1024 bytes of zeros. So what we'll do then is we'll create a block of memory, var bytes. This will be 1024 bytes, which will be more than sufficient for our unit tests. But then these bytes, that are ones that are coming out of the assembler, we'll call ASM bytes. And then what we need to do is we need to copy the ASM bytes into the bytes that we're going to feed into the memory. So instead of feeding it ASM bytes, we're going to feed it in this 1024 block of memory, but we're also going to do a copy. And we'll copy the bytes from ASM bytes to bytes. All right. So what will happen is that the resulting array bytes will now contain the original bytes from the assembler and then pad it out with um, enough bytes so that there will be a guarantee of at least one zero instruction after the assembled bytes. Let's fix that. Of course, another approach would be to just emit that 0 byte ourselves, but let's do it like this for now. Oh, we're still failing. Store bytes. Ah, okay. So now it's complaining that there's not enough space. Let's change this to 2020-48 then, and run it again. And what do we see? A glorious green bar. All the tests are passing. But most importantly, does our program still run? So let's try running it. Let's see what happens. That's really good. So now that we've done all this work, we should be able to tell the linker to link the program somewhere else in memory. We should be able to tell it, listen, I want you to move this program to change the base address to, say, this address. So if we do that, our expectation is that this should work. Let's give it a shot and see if that indeed happens. But now we explode. Why did we explode? We're exploding inside of the linker. The linker is trying to relocate, but remember that the relocations have to happen at addresses, and right now the linker is relocating at offsets. That's a problem. So let's take a look at the linker, and let's see how we can fix the problem. So the problem is happening here inside of relocate. Everything that we are calling the relocation.address, that is in fact not a real address. It's an offset within the section of the assembler section. We really should be calling these things offsets. So let's do that. I'm going to call this offset. Okay. But an offset is not an address. We need to give this relocation the actual address that we're relocating to. So let's go back to our constructor here, and we need to hang on to the base address. Let's give this a better name, actually. Let's call it base address. or new adder base, speaking Hungarian today. And then here, we set up a member variable for the address. And then, in all the places where we do relocation, the relocation actually always has to, or the offsets of these relocations always have to be offset by the base address. So when we read a byte, we find the relocation offset, and then when we write it, we have to do the same thing. In fact, let's compute this once. We don't need to recompute it all the time. We'll just call it the address is going to be this expression. This is the place where we're performing the relocation. And then all the places where we're saying rel.offset, we should instead be using the word address. So let's fix those. Okay. That fixes that. Now let's run them again. Unit test should not be affected by this. The linker should still pass. And then when we run our program, okay, we're still exploding. Let's see why. Oh, right. Haha. The emulator always starts executing at address 0. But now we need to change the emulator so that it instead starts at the instruction that we want, or the address we want. So if we go back to our program, we need to be able to tell the emulator, by the way, start at base address. Now, the one way to do this would be to give it an initial address. So let's pass it an initial address, like this. And then we need to change the constructor of the emulator so that it takes base address. Start address. And then the start address is used to initialize. Why are we getting an error here? Oh, typo. We need to initialize our instruction pointer to that start address. All right, now let's try building, and we'll find that both our unit tests and our main program will fail because our emulators need to be passed this new parameter. Oh, this is unit test. So then in that case, we'll continue using the base address of 0. And all right, let's try running all of our unit tests. Looking good. And then run the actual program itself. Nice. Okay, so now we have refactored our program so that it can generate the output of the executable at any address, not just at address 0. And this frees us up to now allocate a stack someplace else. So when we create the emulator, before we feed it the memory, we could, in theory, do this. We'll do a memory allocate, and then we'll give it a stack area. So we'll stack address, and we'll give it a size of, we'll give it a small stack to begin with, and then make that read write. So this will be our stack. And then the stack top, actually let's call this variable stack size. Okay, and then we need to initialize the stack pointer. The stack pointer right now is pointing at someplace in low memory, which no longer exists because we've moved our code to a different address. We want this to point at the last word of the stack. So that will be stack address plus stack size minus 4. And we'll just write a comment here. Make stack pointer point to last word of stack. And then we need to set up these two variables. And let's consult the diagram that I drew here. I wanted the stack to be at this address, so let's grab that. Nice, and then we want to stack size, so const uint stack size. Let's give it a small stack. Stack size. Not sure why I didn't type it correctly like this. And this needs to be cast to an int because that's the way of the C# language. Now our program doesn't actually use the stack as it is right now. It never calls a function, it only calls system calls. But in essence, if we did, we should be okay now because we've initialized the stack register correctly. Okay, let's do a final run. And we get our hello world as expected. So the refactor seems to have gone well. Our code is now much more capable. And this sets us up for the next session when we're going to introduce command line parameters to our emulator. And once the command line parameters are implemented, we have a system that is about as capable as very early Unix systems back in 1971 or so. And then we will change a little bit of direction in this series once we reach the point where we can stably run programs with command line parameters. We can do some file I/O. So then we will look at some interesting applications of our capabilities. But for now, I will sign off. Thank you so much for watching, and keep coming back for more Risc-V emulation. Bye.